Good evening, students who follow the course of mathematical physics. I hope that you already started to follow my lecture on Heisenberg uncertainty relation, yeah? One of the basic relations in quantum mechanics. I would like to make some comments to this lecture because there were some notations which are used in physics but not so common in mathematics, and there can be some difference. So there's Paul Dirac, English scientist who did a lot in quantum physics, and he introduced some notations which are very natural from some viewpoint. So he thought, let us denote vector. So this is vector from Hilbert space H, yeah, vector from Hilbert space H. Let us denote this vector not just f, but in this way. So this is just symbol, This symbol is convenient to write scalar product. So if we write scalar product, we write here one vector, comma, another vector. Here they do the following. They take this vector, put here, and in some way symmetrically reflected vector put here. So this is the same as we write this scalar product. So in principle, you can forget about this notation of vectors, but just accept that in physics, instead of comma, they write vertical line. But this vertical line is coming from this Dirac notation. Now, if we take some complex number, we can denote such matrix of operator A multiplied by unit operator. Unit operator, so its matrix is just diagonal matrix with A on diagonal, rest are zeros. In my lecture on Heisenberg, there was expression operator A minus average A. It's the last term should be a bit more explained, because this is operator or matrix, and this is number. Of course, we cannot subtract from matrix number. So in fact, this expression, or in fact, it's the second part, it has the following meaning. It's operator, it's okay, minus not just number, but this number, this play the role of this A, multiplied by unit operator. So all expressions in the lecture of Heisenberg, where we have operator minus average, in fact, should be understood in this way, yeah, should be interpreted in this way. So operator minus average multiplied by unit operator. Okay. In physics, they often put hat over operator. In some way, points that this is matrix or operator. So linear operator. Matrix is just representation of linear operator. I don't know whether you had this notion in algebra. I really hope that you had course in linear algebra. So, but for your convenience, I recall you what is linear operator. It's a map from linear space into linear space, such that it put the sum of two vectors into the sum of images. And if you multiply vector by complex number lambda, it can go out, and it will be lambda multiplied by A applied to this vector. Here, F and G vector from Hilbert space, and lambda is complex number. Good, good, good. Now home task number 3. Home task number 3. Please select your own matrices A and B, 2 by 2. Any two matrices which are not commuting. The commutator AB is not equal to 0. It means that AB is not BA. Well, it's easy to find two such matrices. Do this. Then take the states that we had in home task number 2. Very simple state. Then calculate the average and average of B by this formula. This is in physical notations, vertical line, and this is mathematical comma. Then calculate dispersions. Then calculate the average of commutator. So it's by this formula. Then calculate the average of anti-commutator. And then put all these numbers and check that Shcrödinger inequality is really correct. So that for you two non-commuting operators, A and B matrices, but 2 by 2, simplest matrices, the product of two dispersions is less or equal. In another part, we have the absolute value of average of commutator squared, average of anti-commutator squared. No, you can look to this equation, to the Shcrödinger inequality in the previous lecture. So this is all for this very short, even not lecture, but comment.